All right. So last time we gave a brief introduction of diffusion. I put a bonus video up there looking at diffusion in coffee. So today I want to get into the specifics of different types of diffusion, and we're going to start with the simplest case called steady state diffusion. So the first concept we need to look at when we look at diffusion is the idea of mass transfer and quantifying that mass transfer. So we're going to look at measuring this by looking at the rate of mass transfer, and then that's per unit of surface area, and we call this the flux. So this is defined as the mass, or you can also talk about the moles moving through a given area. So that's the red portion here, and then the green, even though it says E, this is the mass. This is just a better image for it. And it's doing that per length of time. So how much mass passes this area per length of time? That's the definition of flux. And you may have heard this term flux, not only in terms of mass, but you can also talk about electric field, which is what the E actually means here, but we can use it in the same context, or magnetic field flux. It really can talk about anything, but the important things here are that it's normalized by area and it's over a length of time. So the units for us are going to be kilograms or grams, or it could be moles per area. So meter to the -2, so it's over meter squared, and then over seconds, so second to the -1. So those are our units that we're looking at, and we term this with a capital J. As flux, and this is basically just a formula of what we talked about up here, and again just going through the units that we can see. So either moles or mass, and then area seconds. All right, so when we're looking at this area that the flux goes through, we can think of this as a membrane because mass is going through it, and that's what a membrane is. And so we have our definition of flux here, and we want to look at the flow, and we want to look at that flux for a specific experiment. And so the reason behind the movement of this mass is if there is a concentration gradient imposed, right? So the concentration is really high on one side, really low on the other side. So in the example of the coffee, right, all of those molecules are in the coffee, none of it's in the water, and so there's this driving force for it to diffuse into the water where that low concentration is. Same thing with the dye. If you look at a dye droplet in a beaker of water, it will expand out because the concentration is low. So that's kind of the driving force. So when you see concentration gradient, that's what we're talking about, a difference in concentration over this area. And so, so we can measure this empirically, with an experiment, right? We can look at a thin film or a membrane of a known area. We can impose this concentration gradient, and we can measure how fast the atoms or molecules diffuse across that membrane, right? So this is something that we can very much quantify looking at what we have down here. And so the idea with this experiment is that, again, in this case, we're talking about steady state diffusion. So what we mean by that, when we look at this, is the steady state means the rate is time independent. It doesn't change with time. And so here's the kind of the experiment here shown visually. So this is the high concentration side. This is the low concentration. So the driving force will be to have the concentration or the molecules in A go towards the low concentration side, which is C2, and this is our membrane. It's with a given area, and it's also a certain thickness. And so we're looking at how quickly the mass travels from one side to the next. And what we find is that it doesn't change with time. So the rate is always constant in this case. And that's known as steady state diffusion. So the flux is proportional to this concentration gradient, and we define this concentration gradient as the difference in concentration over the difference in thickness. So dc dx, where again this thickness is the x. And so we can use this to formalize an expression for how the flux is related to this concentration gradient for this steady state type of problem. And this is known, what's known as Fick's first law of diffusion. So Fick's first law talks about steady state diffusion. And what we see is that the flux, so again, that's mass that goes over an area, a known area in some length of time, is proportional or is equal to the minus of this constant term d, which we're going to talk about more, multiplied by the concentration gradient. And if you're wondering why we have the negative is to show that the flux goes from the high side to the low side, right? This is just to show what naturally occurs. So that's why we have the negative. And so the flux is proportional to the concentration gradient. So the higher the difference of concentration, the higher the flux, and then also the higher this term is, the higher the flux. And this term d is known as the diffusion coefficient, and this is tied to the material itself. And so we'll definitely talk more about this, but this is kind of a material property at this point. And so if the concentration gradient is assumed linear, then we can find that concentration gradient by simply taking C2 minus C1 over X2 minus X1. That's our concentration gradient. And again, that's assuming it's linear in this case. All right, so let's kind of think of a situation where this steady state diffusion may be a good approximation. And let's think about basically lab gloves or rubber gloves that you use either around the house or in the lab when you're doing experiments. The idea of the rubber glove obviously is to keep chemicals away from your flesh, away from your hands. So the specific example here is methylene chloride. This is a common paint remover. It's also an irritant, and so it can absorb through the skin and cause irritation. And so you want to use gloves to protect you from that. And so we can take a look at butyl rubber gloves at a certain thickness, and we want to look at the flux across that thickness and see what's going to happen to our hand, right? So we're given that diffusion coefficient for butyl rubber. We're given the concentrations of the chemicals on either side. And then we're given the thickness up here as well. So we can basically set up this problem where the paint remover is the high concentration side, our skin is hopefully the low concentration side, and the thickness is represented by X2 minus X1. That's the glove. And so we can set up this problem. We can set up the concentration gradient. We know the diffusion coefficient, and we're looking at the flux. And so if we plug in all those values that it gave us, D, which was in units of centimeter squared per second, the concentrations were in grams per centimeter cubed, and then the thickness was in centimeters as well. If we plug all that in, we get a flux of 1.16 times 10 to the minus 5 grams per centimeter squared second, right? So units of mass area second. So that's our flux. And so that kind of tells us how much is going to go through that rubber glove. And that's an important number, right? If we want to compare different gloves, then we would obviously want to pick the glove that had the lowest flux, because again, that flux means mass of that chemical that's an irritant getting to your skin. And so that's an important calculation. But again, I want to emphasize here that we're assuming the rate isn't changing. So the rate, the flux is constant with time. for this experiment. And so in the next example in the next section that we're going to talk about in terms of diffusion, we're going to look at when that's not an appropriate assumption to make, and that will be non-steady state diffusion. But first, we're going to look at an example in the next module.